Howdy, students. This is lesson 4 of chapter 15 and 16. Our objectives today is to continue exactly where we left off on lesson 3, which is going to be calculating a titration curve for a weak acid strong base. Now, in lesson 4, what we're going to be focusing on is the exact opposite, a weak base with a strong acid titration. So make sure you give yourself time to pause the video, calculate the stoichiometry, calculate the equilibrium tables. Always pause if you need to catch up, because we're going to move swiftly through these points. Okay, so the first thing that we need to look at is the titration curve for a weak base strong acid. You'll notice that the curve is flipped. Instead of starting at a pH below 7, we are starting at a pH above 7. And in this one, probably around 11, maybe above or below, depending on the concentration. So before the equivalence point, there is going to be an equilibrium system for a weak acid and base. So when we make an addition of an acid to a weak base solution, we're going to have to actually go through the chemical reaction to figure out how many moles of acid and base remain, and then we can set up our equilibria problem. At the equivalence point, an acidic salt will be present, which is going to turn around to react with water, which will actually lower the pH below 7. After the equivalence point, the strong acid is the dominant species, and we'll see a sharp decrease in pH because of the high increase in concentration of H+. One thing I'd like you to write into your notes is the general equation for the reaction of a weak base and a strong acid. So our base plus the strong acid H+, and a one-sided arrow is going to form BH+. Now, depending on the weak base, the plus sign may be there, it may not be there. But either way, let's go ahead and write in that general equation for what's happening here. This will be used in our BCA table. Okay, let's go ahead and move on. We're going to plot our points. The first plot that we're looking for is going to be the point where we start our titration. And we're looking for the pH. We're going to have 50 milliliters of a 0.050 molar ammonia solution, and we're going to titrate it with a strong acid, 0.10 molar HCl. And we are given a Kb, of course, because we have a weak base in ammonia, 1.8 times 10 to the negative fifth. Currently, at the start of the titration, there's no addition of strong acid, so we only have a weak base present. And so we don't need to do a BCA table because there is no chemical reaction happening. So let's go ahead and start a Rice table. Now, this is where students get confused and say, I don't know what equation to write. Okay, well, let's look at what we have. In H3, if that's a Kb expression, we're going to have to include water into that expression because we need to show the base accepting the proton from water in order to produce ammonium and hydroxide ions. The initial concentration is given for ammonia, 0.050. We're going to leave out water, standard minus x and plus x. We get our equilibrium values. We're going to use our Kb expression because hydroxide has been produced. I'm going to highlight the negligible x here in our Kb expression, products over reactants. And then we're going to cross multiply, and we do have to take a square root of both sides in order to get the hydroxide concentration, which is 9.5 times 10 to the negative fourth. We're going to get the POH from this number, and then we can do 14 minus the POH to get the pH, which ends up being 10.98. So currently, at the start of our titration, we have a pH of right around 11, which is what we saw from the graph. So let's go ahead and plot our first point. 0 addition, and I'm going to go ahead and change. There's a mistake here. This should be amount of HCl added because this is now our titrant. First plot point goes at 0 and 11. Okay, let's move on to our next point. Calculate the pH of the solution after 7.5 milliliters of strong acid HCl has been added. Add this point to the graph. So first thing we need to note is that strong acid plus weak base, we do have a chemical reaction, and we are going to have to set up a BCA table for this. So let's jump in. We need the moles in order to plug into our BCA table. Liters times molarities gets us moles of weak base. And this is going to be the same for each problem and each point that we do, because what we're changing is the amount of strong acid. So let's look at how many moles of H plus are being donated by the strong acid. 7.5 times 10 to the negative fourth. So again, this is where students get stuck with the BCA table. What equation am I writing? Remember that moles is the only thing that we can plug into our BCA table. We're going to write out NH3 plus H plus yields NH4 plus. And remember, this is the generic form for the reaction of a strong acid which donates H plus to a base that accepts a proton. So this is what our BCA table will look like, single-sided arrow. We're going to plug in our mole values, 0 for ammonium. We're looking for the limiting reagent, which in this case is the HCl. So I'm going to make a note that this is the limiting reagent, which we will consume all of the H plus at the beginning of our titration. Makes sense. We haven't dropped the pH below 7 yet. So after we have our mole amounts, only weak base and conjugate acid are left. There is no free H plus. So we can use the Kb expression because that's also what we were given in the problem. So let's go ahead and set up our rice table, which again is for concentration. So make sure you are dividing by total liters of solution. We have to write the Kb expression. Our initial concentrations are 0.030. And where did that come from? Well, if we look back at our problem, we had 50 milliliters of the ammonia solution. And then we're adding it to 7.5. So total liters would be 0.075. So we're finding molarity here, moles per liter. There is no hydroxide to begin with, and we don't include water because it does not affect our equilibrium. Minus x and plus x. Here are our equilibrium values. We're going to have two negligible x's when we set up our rice table. When we get rid of those, we will be cross-multiplying and dividing. No square root. And what we find is the x value, which is the hydroxide concentration, which is what we were after in the first place. And let's go ahead and calculate pH from, remember, we got to do POH first. We get a pH of 9.62. So let's go back. Let's look what happened. First point, before the titration, pH of 11. First addition of 7.5 milliliters, we get down to a pH of 9.62. It's dropping, but it's not dropping below 7 yet. Makes sense. Let's plot this point. And again, these aren't going to be perfect, but do your best. After 7.5 milliliters, we are dropping our pH just slightly. Okay, moving right along. We're going to calculate the pH of the solution after 12.5 milliliters of HCl is added. So we're adding even more. And remember, we're going to assume that we're starting the titration from 0 milliliters of HCl addition. Why? Because then we don't have to back calculate anything. And we're just assuming this is how much we've added from 0. Okay, same amount of moles of ammonia to start out with. New amount of H plus moles. Why is it more? Because we've added more strong acid. BCA table remains the same. We are plugging moles. H plus is still our limiting reagent. And this is the change after the reaction has occurred. Now, there's a mistake here. I want you to fix it. This should be a single-sided arrow. 50 milliliters plus 12.5. We have 62.5 milliliters of solution. So when we plug in to our rice table, we're going to make sure that we do moles per liter. At this point, what we see is something pretty special. We have equivalent amounts of weak base to conjugate acid. And remember, when the concentration of weak base to conjugate acid is identical, we find ourselves at what we call the half equivalence point. And we can actually calculate the pH of the solution from the pKb. So we don't need to use a Rice table here, but if we did, we would use the molar amounts. So if I take the negative log of the Kb value, that's going to give me pOH, and remember, this only works at the half equivalence point. The pH ends up being 9.26. So we've dropped a little bit more, but this is at the half equivalence point. Let's go ahead and plot that point. First two, and then we're going to drop just slightly. And what I'm going to note here is that we have a sharp drop, but then it's going to kind of level out. We call this the buffering zone. When you have equal amounts of weak base conjugate acid, this makes a great buffer. So this is why this portion of the curve will end up being a little bit longer. Okay, next, let's add 25 milliliters of HCl to our solution. Okay, moles of ammonia are the same. That is the analyte, and we have 2.5 times 10 to the negative third moles of H+. We will probably start to have some excess of H+ here. BCA table, we're going to throw in our molar amounts. Now, looky here. What we have is an equal amount of H+ with weak base. So at this point, there is no limiting reactant. We have no excess of reactant anywhere. Both of these amounts end up being 0. So it appears that we have reached the equivalence point. But what do we know about NH4+? Well, from a weak base, that makes it a strong conjugate acid. And a strong conjugate acid will attack water. And we need to recalculate the pH there, because it won't be exactly neutral at 7. Only conjugate acid is left, so let's use a Ka problem here. Now, we were given Kb, so you will have to interconvert between the two. We're going to write a Ka expression where we have the acid dissociating into ammonia and H+. I'm going to use molarity. Our total moles would be 50 milliliters plus 25 milliliters for 75 milliliters. And remember, we have 0 amounts of dissociated conjugate acid. The change, minus x and plus x. Here's equilibrium. Now, again, this is a Ka value. So I had to calculate from Kb doing 1.0 times 10 to the negative 14th divided by the Kb, which gave me the Ka. We have x squared over 0.033. I am going to get rid of the negligible x. Cross multiply, take the square root. We get the H+ concentration now. Please be careful. So many students forget if this is OH or H+. You got to figure out what you're solving for. From here, we can get the pH. And man, what a significant drop from 9.26 down to 5.37. That is significant. So when we plot our first few, we're going to have this really sharp decrease. So initially it dropped, kind of hit that buffering zone, and then boom, it's going way down. So let's see what happens now that we've reached the equivalence point. What happens when we continue to add more strong acid? So let's add even more. We're going to go 35.0 milliliters of HCl. Moles of ammonia are the same. Even more moles of hydrogen. Our BCA table is still the same. One-sided arrow. We're going to plug in moles. Our limiting reagent now is the ammonia. So now we have switched our limiting reagent. We have an excess of H+, which is going to drop the pH even more. And we also have a conjugate acid. So there's a double decrease in pH. Only the strong acid and the conjugate acid are left. So in this case, what happens is the H+ from a strong acid is going to be our source for H+. So yes, the conjugate acid is there, and perhaps it has a slight effect, but the H+ I'm going to go ahead and use what I did in the previous video. This is going to contribute so much more than the weak or the conjugate acid. So we're going to take the concentration of the H plus, and we're going to find the pH from that value. pH really drops here down to 1.93. Plot our points. There's equivalence, and we're going to drop even more. So we drop, we've got this buffering zone, we drop for the equivalence, and then strong acid should start to level out. Last point, we're going to go a little crazy and add 50 milliliters of HCl. Ammonia is the same. We have even more moles of H+. We're going to throw in the values for moles into our BCA table. Once again, ammonia is our limiting reagent. We have even more. And remember, the concentration of these guys is going to be way greater than what it's going to contribute for the conjugate acid. So we can take the concentration of H plus at 2.5 times 10 to the negative 2. And on the last example, I don't think I mentioned this, but remember, this is moles. We want moles per liter for concentration. So you have to divide, and this one is 50 milliliters and 50 milliliters, which makes for 100 total milliliters, which is why the exponent changes there. Take the pH of 1.6. It's starting to level off. So if we go ahead and graph this, come down, buffering zone, equivalence point, and then it's going to start leveling off. Okay, and that will do it for this video.